An analog modulator is explained and its circuit operation is analyzed in this example, that is the 212 video in the circuit analysis and design playlist. The circuit is serving three inputs, V1, V2, V3, that are three small signal voltages. There is 10 volt and negative 10 volt bias in the circuit. And then at the output, we have voltage V out that I am going to show it's proportional to the product of V1 and the sum of V2 and V3. Basically, V1 is serving as the modulation of amplitude for V2 and V3, and hence the name analog modulator, which is employing sort of analog multiplier. I'll show that this proportionality coefficient is something like RF over 2 times R times VT, where RF is the feedback resistor here, and R is the main resistor in the circuit. And VT is the terminal voltage of PN junction of BJT transistor, which is roughly about 25 millivolt at room temperature. I'll talk about it briefly. So we want to do a quick analysis to understand how the circuit is working, the quick DC analysis, and also a very fast, hopefully a small signal input-output voltage formula calculation to show and prove that this is the case. So that's the plan. Okay, so the first thing to do is understanding how the DC in this circuit is working. At the bottom of the circuit, you can see we have negative 10 volt, and there is a voltage divider between these R and R. So basically, as a result, there will be negative 5 volt at this node because no DC current can flow this way, because one, it will hit the positive terminal of op amp that cannot take current, and then the other one will hit the decoupling cap that is basically separating DC, and DC cannot flow through it. So we have negative 5 volt here. As a result, that negative 5 volt appear at the positive terminal of input terminal of the op amp, and because op amps are properly biased, meaning that the op amp 1, 2, 3, they are properly supplied with the plus 10 volt and minus 10 volt supply in this example, and they are properly biased. So the virtual short will be there with guarantee that the voltage at positive and negative terminal is the same. So if we have negative 5 here, we have negative 5 here, negative 5 here, we have negative 10 at this node. Therefore, the DC voltage across this resistor is 5, and it means a current of 5 divided by a current of 5 volt divided by R is passing through this resistor, which can only go this way. So, and that means assuming that these transistors that are, let's name them T1. So this one is named transistor BJT bipolar transistor T1 N-type, NPN, and then T2, and let's name this one T3 and T4. And of course, we have two other transistors at the bottom of the circuit, but T1, T2 would be, they are selected to be matched transistors, and therefore half of this current will, DC current will go through T2. So I'm going to show it this way. Half of that goes through T2, and half of it, so that would be basically 5 divided by 2R. And the same situation will be here as well, because negative 5 appears at the negative positive terminal, again because of virtual short, which enforces positive and negative terminal of the op amp to be the same when op amp is operating properly. So that negative 5 appears here, and the same story keeps happening. So the voltage drop across R is 5 volt, therefore the current is 5 over R. That current is flowing this way, and as a result, half of it, because of matched transistors, then half, which are in the same die and package, then these transistors will have half of that current. So I'm going to show it this way again. There you go. So half of that current is going to, maybe I'll show it this way. There you go. So 5 over 2R is passing through transistor T3. The reason I'm focusing on T2 and T3 is because, as you can see, the branching out, this node, and the branch out toward outside the final stage of the circuit, and this node and its branch out toward the final stage are the ones that matter to us. Okay, so since we have 5 over 2R passing through this 2R resistor, therefore the voltage drop across this 2R resistor will be simply 5 over 2R times 2R, which means 5 volt voltage drop across the resistor. So this voltage drop is 5 volt coming down from 10 volt. It will cause or result in plus 5 volt at this node, DC. And the same thing is applicable for this node as well. So here we'll have or to be more accurate, here we have 5 volt as well. Okay, so at least we know what is the DC contribution at those output or let's say near output nodes. And look at the decoupling caps we have. So those decoupling caps would separate and decouple DC from the rest of the circuit. For DC analysis, there is no current that passes through R here, because as I said, decoupling caps are preventing DC to be transferred. So there is zero DC current, and therefore there is zero DC voltage here. As a result, effectively this becomes like a buffer and zero DC voltage here, and therefore V out is zero DC. So no DC voltage shows up at the output. Okay, so with that said, now let's just see what we can do about the AC, which is the main focus of the circuit. Okay, so we have, let's focus on AC side. First, look at what we have for V3. That's a small signal. So what I mean by small signal, I mean, for example, V3 is in the form of a sine, let's say, omega t. For example, it can be audio signal. So omega is 2 pi f. So let me actually write 2 pi f. 2 pi f, in which f is in hertz, and then t plus some phi. And then this f, if it is audio signal, we expect the f to be in the range of, say, 50 hertz or 100 hertz at lowest side, up to, let's say, 20 kilohertz. So if it is in audio application, but it can be adjusted accordingly. So with V3 being a small signal, I mean the A or amplitude is small, for example, on the order of, let's say, tens of millivolt, as an example. So with that said, now let's focus on what's going on. So V3 is coming here, but there is a bypass cap here, which is, for example, a 10 microfarad cap. So as an example, 10 microfarad. And this would actually cause an AC virtual ground here. So it would short this node to ground AC-wise. So let me show it this way, virtual ground. And as a result, what happens is that V3 will appear, of course, mainly here. So there's a direct connection. This bypass cap, this decoupling cap actually is shorted AC-wise at the frequencies of interest. And so V3 is just directly connected to the positive terminal of op-amp number 2. So here we have V3. Let me change the color. I'm going to remove the -5. So the DC analysis was done. No need for keeping them. So V3 is here. And then as a result, V3 is also here. And then V3 is here. And because we have a bypass cap here, it would actually cause this node to be AC virtual ground. So what it means is now on top of the DC, we have a V3 drop across R AC-wise. So therefore, as a result, we have plus minus V3 across R. So there is on top of the 5 over R, there is a AC, a small signal current passing through this resistor R, which is now equal to, let me just write it here, which is now equal to V3 over R. Okay, that V3 over R cannot go this way, again, because the input terminal of op-amp cannot serve any current because of infinite impedance. So that would just go this way with the direction that is shown default. And so that's what is coming from this branch at the bottom. Okay, so what else do we have? So let's keep this as, let's say, the value of this current, as far as we can see, is 5 over 5 plus, so we have the sum of these two currents. So this common branch current that is coming downward from the emitters of the NPN transistors T3 and T4 would be just 5 plus V3 over R. So let's keep that in mind. Now let's move on to V2. It would be very similar. So V2 is connected via a decoupling cap, which then at the frequency of interest is shorted. So V2 is here. Now, I just mentioned that because of bypass cap 10 microfarad at this node, its effect, which is connected to positive terminal of the op-amp, then it's effectively AC grounded. So positive terminal is AC grounded because of virtual short. Then we have negative terminal AC grounded as well. So when negative terminal is AC grounded, then what happens is there is just a simple voltage drop V2 across resistor R, and hence there is an AC current. That AC current is equal to V2 over R. And there is only one way for that AC current to go. It cannot go through the negative input terminal of the op amp because of infinite impedance, so that AC current can only go this way. But now here's the next catch. The next catch is that AC current can only go one way, which as a result, that is what is shown here, is because this node, which is this node as well, is AC grounded, and AC grounded also here. So AC wise, nothing can go through R because both sides of R are AC grounded virtually, and therefore this current can only go upward with this direction toward the emitter of transistors T1 and T2. Okay, so what can we do about it? Well, there are two currents going through this route. One is the AC current that I just showed you, which is basically V2 over R, and toward up with default direction as long as V2 is positive. And the other one is the downward current, which is 5 over R. So therefore, in contrast to 5 plus V3 over R, the total current here is going to be 5, and then we have minus V2 over R. So because of the direction. So arbitrarily, we make the assumption that the direction for the current is just downward. So with that, because the blue one here is upward, we have a negative sign for it. So 5 minus V2 over R is this total current. All right, so this is important because now in order to do the AC analysis, let's focus on the differential pair of NPN transistors here. So what we have is something like this. I'm drawing this portion so that it's easier to see what I'm going to show. There you go. So this is the AC ward, and then AC ground. So for the resistor R, and then we have resistor R, we have transistor T1, and then we have sort of this scheme. So we have a combination of DC and AC current. So 5 minus V2 over R. So the 5 over R portion is DC contribution, and the minus V2 over R is the AC contribution for the current, which is a small signal, for the current that is going this way effectively. And then we have transistor T2 and the desired output. The desired output is what? And then it's grounded on the other side. So in the sense that we don't care on the other side what is going on, because what you can see is on the other side we have the parallel of these two resistors, because on one side is virtual ground, on the other side is virtual ground. And so if you want to be super accurate, we can see that voltage via this decoupling cap, voltage V1 is connected to this node. So therefore we have V1 here. So let me draw it better. So we have V1 here, and then we have the resistor R and resistor R, effectively with virtual grounds. So that's the scheme we have. I don't care about those, but what happens is V1 effectively appear across this portion, as you can see. So V1 is applied to the base of transistor T2 and ground. So I can say V1 is like this, between the base of two transistors effectively. And then on the collector of T2, we have 2R connected to 10 volt, effectively AC grounded on top. And then we have via this wire and this decoupling cap, which is shorted at the AC range, then AC frequencies, then we have connection to R. Okay, so to show that, I am going to just show them here. We have resistor 2R, sort of virtual AC ground, and then we have a connection outside, and we have that resistor RF. So this one should be RF. Okay, so this is the scheme we have for the first set. We have exactly same scheme for the second differential NPN BJT transistor pair here. So I'm going to copy paste what I showed you here. I'm going to copy paste it. There you go. and I am going to show exactly same scheme. So what we have is, we have transistors. Let me just clean up. So we have transistors T3 and T4 on top here, T3 and T4. And the connection is not like this. The connection is, so I don't care about T4 for the time being, but the connection is, we have connection to 2R resistor, again AC grounded, virtual ground, and then we have go down, and then we have connection to the op amp at negative terminal, which is then going to its output with resistor R, F. So we have that scheme. Okay, so what can I do now? So it's not, and also the value of this current is not 5 minus V2, it's 5 plus, as we talked about it, is 5 plus V3 over R, 5 plus V3 over R. Okay, so now it's easier to see what is going on. We have an AC current, AC voltage here, and that AC voltage is appearing across the 2 base emitter PN junction, and then a small resistor R. The value of that resistor R is also shown here, is 100 ohm. It's pretty small. We can neglect it. I'm going to show. So this resistor R is just simply 100 ohm. And let's take a look. Just take a look at V1. V1 appear across 2 base emitters. So as a result, I base AC is I base 2 is passing through this circuit. So I can say I base 2 is equal to the total voltage is V1 divided by there is RB or R base of this transistor and RB and R base of this transistor. Because they have the same DC current because of what we discussed as matched transistors, then therefore I can just say the same basically bias current. I would just say it's going to be 100 ohm, this guy, in series with RB1 and RB2, which means 2RB. So it will be plus 2RB. Okay, now, as I said, just to give you a sense, RB is by the resistor seen at the base for the PN junction is simply the thermal voltage VT, which, just as a reminder, VT is KT over Q. K is Boltzmann constant. T is the junction temperature in Kelvin for the PN junction of the BJT transistor, and the Q is the electron charge. So at the room temperature, when T is roughly 290 degree Kelvin, corresponding to about 17 degree or close to 20 degree, this number is something on the order of 25 millivolt for the thermal voltage. So that's just giving you a sense. Now, with that said, RB is VT over I base of transistor. Now, the current of the base is half of this current. So what I'm trying to say is, if you just take a look at the range of value for this, so it would be VT over, let me just write it here, it's better. There you go. So just give you a sense of comparing the value of RB compared to 100 ohm, which is going to be considerably larger, practically speaking. So VT over IB is IC of the transistor at I emitter of transistor divided by, say, beta plus 1. And then as a result, which we can just say beta, because beta is for these small signal transistors, let's say on the order of 200, which is very nominal value. And then we have, so roughly VT beta divided by I emitter. I emitter is half of this current, because half of it goes through T1, half of it goes through T2. So as a result, I can say it's VT beta and then 5 minus V2 divided by 2R. So therefore it becomes 2R beta VT, and then we have 5 minus V2. Now, just to give you a sense, assume that R is 1 kilo ohm, a nominal value for this resistor R that is spread throughout this circuit as a default core resistor. As you can see, it's repeated many times. And then beta, let's say 200, VT is 25 millivolt, And V2 is negligible because it's a small signal compared to 5. So effectively, you can say, just for the sake of getting a sense of the ranges, so we have 1 kilo ohm times 25 millivolt. And then for that one, we have, say, let's divide 25 by 5. So let me just write it this way. So 2 times 1 kilo ohm times 200 times 25 millivolt, and then divide by 5 in the denominator. So we have divide by 5. So this becomes 5 millivolt, and then times 200 is 1000 millivolt, which means 1 volt. So effectively, we end up with 2 times 1 kilo ohm, so 2 kilo ohm for, in this example, for RB. So 2 kilo ohm times 2 compared to 100 ohm. So that's why I'm saying it's considerably larger, so we can neglect the 100 ohm effectively. So this is equal to V1 divided by 2RB. This is the formula that I really need. I'm going to expand that formula here. So IB2 is equal to V1 divided by 2RB. I'm going to use this formula that we have. So it will be 4 times R beta Vt divided by 5 minus V2. So as a result, what we're going to get is just V1 divided by 4 times R beta Vt times 5 minus V2. That's IB2, basically this current. Obviously, the corresponding IC2, which is what I care, is going to be IC2 is going to be beta times IB2, which is beta is the current gain, or HFE, of this NPN transistor. So it's going to be beta times this value. And if you multiply that, beta and beta cancel out each other from numerator to denominator, we get V1 over 4R Vt, and then we have 5 minus V2. Okay, so that's the very important formula I really wanted. So with the same argument, we can apply exactly same analysis to this one here as well. So we did it for this portion of the circuit, which means for the first core, sort of Gilbert cell cores. And then for the second one here, I can apply the same analysis, and then I will get, as a result, this outcome that says IC3, or basically the corresponding AC small signal current going through the collector of T3, is equal to, this time, V1 divided by 4R Vt, and then we have 5 plus V3. Because previously we had 5 minus V2, so 5 plus V3. So let's name this equation number 3. All right, let's simplify the circuit now. To further simplify it, to see things, remember, there is IC2 that is basically coming out of this node, with 2R connected to ground and RF connected to ground. And on the other side, we have IC3 as a current source that is connected to 2R and also connected to the op amp with RF in the feedback resistor. So I can just show the circuit like this now. So therefore, we have, let me show the circuit like this. So what we have is, I'm going to draw it here. We have the op amp. We have the negative input terminal, positive input terminal. So negative input terminal is connected to the output via RF. And this is Vout. Then we have a connection to, so I'm going to show it this way. The positive terminal is connected to resistor RF. And also on the other side, we have the connection to resistor 2R, AC grounded, instead of in lieu of 10 volt fix. And then we have this current that has this AC current has two contribution for IC2. So IC2 has two contribution. One is V1 times 5 divided by 4R Vt, which is V1 is a small signal, so it's positive, so by default. So it's going down by default, 5 V1 over 4R VT. And the other one is the one that is negative value because it is V1 times negative V2. So for that one, we can remove the negative sign by change the direction. So I'm going to put it this way. Default direction is like this. V1 times V2 divided by 4R VT. And for the other one, we have similarly same setup. We have effectively two currents. So both of them going down. So 5 times V1. So we have 5 times V1 divided by 4R VT, and we have V3 times V1 divided by 4R VT. So we have this one, and we have this one, and then we have connection to top, AC ground, and then we have 2R. Okay, so the value of these resistors are, this current sources are V1, V3 divided by 4R VT, and then for this one we have 5V1 divided by 4R VT. Now the nice thing is with this setup, which is effectively the small signal equivalence of the output of the circuit, what we have is this situation. Due to symmetricity of the circuit, which is 2R and RF, and effectively 2R and RF, and the fact that op-amp will try to force virtual ground, so basically op-amp will try to force V plus equal to V minus, sorry, virtual short, so virtual short. Then what's going on is, for the current 5V1 divided by RVT, and the same current for 5V1 divided by 4RVT that is present with the same direction in both sides due to symmetricity, since on the positive side, positive terminal side, we have that current contributing to the connection to our RF, with RF side grounded, AC grounded, and then we have exact setup. Therefore, the contribution of that to V out should be 0 to match that symmetricity. What I'm trying to say is, if we apply superposition, basically for a moment neglect by opening these two currents and just focus on contribution of these guys, we can see that due to circuit symmetricity and the fact that op-amp will try to enforce the virtual ground, which will enforce that the voltage here and the voltage here are matching. Therefore, we will end up with, as well, the voltage here and here should be matching, which means the voltage V out should be 0. So basically, what I'm trying to say is these two current not contribute anything to the output. So I can basically just forget about them. That's the beauty of sort of intuitive analysis. So we can let go of these currents and forget about them. They're not contributing anything to the V out. The only thing contributing would be these guys. Let's name them as IX and IY, just to make life easier. Now, IX is, of course, flowing through 2R, a portion of it, and a portion of it flowing through RF. Since op-amp is forcing virtual short between the positive and negative terminal equal to, let's say, V, therefore the voltage here is V, and the voltage here is V as well. Since it's the same voltage V across 2R and the same V voltage across 2R, they should have the same current. So the same portion of IX that goes this way should go this way as well. So I'm going to show it here. So this is, if what we have at the bottom here, so let me move this value to R to the other side so that things are easier to follow. Okay, so if we have basically here alpha IX, we should have alpha IX here as well. Now things are easy because here we have IY. At this node, effectively we have IY going down and alpha times IX going up. Given KCL, and given the fact that nothing can go through the negative terminal of the op-amp, then the current here should be the sum of alpha IX and IY. So I'm going to write that exactly. So this I out, let's name it I out. I out is equal to alpha times IX plus IV. Let's substitute. Okay, so what do we have? For alpha times Ix, we have, of course, the current is flowing to two resistors RF and 2R, so it's the current division, and alpha is effectively just RF divided by 2R plus RF times Ix, so that's the alpha, and IV is just IV. Okay, so as you can see, the Vout can be found using KVL or Kirchhoff voltage law. So basically we have two components in Iout. One is the alpha Ix portion, which is flowing from Vout to 2R, because it can't go to IV, because IV is a fixed current, sort of fixed value AC current. So therefore what happened is Vout is equal to the RF plus 2R times alpha Ix plus IV can only go, as we discussed, IV can only go through RF, no other way for it. So therefore we get RF times IV. So in conclusion, we have Vout equal to RF plus 2R, and then we have, substituting for alpha, we have RF divided by 2R plus RF times Ix plus RF IV. Well, we are almost there. 2R plus RF cancels out this one, and therefore you can easily see that we get Vout, so these are Vout, equal to simply RF times the sum of Ix plus IV. Now is easy, because we can substitute the value of Ix here. Let me show it, and also IV here. So if we substitute, we get RF, and we have Ix is V1, V2 divided by 4R VT. And then for the other one, we have V1, V3 divided by 4R VT. So we factor out, we get exactly what we wanted. We get, basically the outcome becomes Vout is equal to RF divided by 4R VT times V1 times V2 plus V3, exactly what we wanted to say. So overall, we can just basically say, since we found the formula that relates output to input, and of course, be careful, it's 4 times, not 2 times, as I said at the beginning. So therefore, we can easily say it means exactly as we targeted. So Vout is proportional, so is proportional. Vout, a small signal, is proportional to the product of, linearly proportional to the product of a small signal V1 and the sum of V2 plus V3 as we desired and wanted and claimed at the beginning of this analysis. That concludes this interesting analog modulator, or let's say multiplier, which is, as I said, utilizing effectively a Gilbert cell-like core to realize this interesting relationship between its 3 input voltages and the output voltage. I hope this is helpful.